Hi all, today we discuss theorem 9. Let V and W be n-dimensional finite dimensional vector spaces over the field F such that dimension of V is equal to dimension of W. Then we have three equivalent conditions. T is linear transformation from V into W. Then T is invertible if and only if T is non-singular, if and only if T is onto. So in order to prove T is invertible, you need to verify one of these statements. Either this T is non-singular, that is 1 1, or T is onto. So it is enough to prove that T is invertible, and vice versa. So first we have the condition is dimension of V and dimension of W should be same. In this case, we have three equivalent conditions are there. The first condition is T is invertible. T is invertible means T is 1 1 and 1 2. T is 1 1 and 1 2. That means nullity T is equal to 0 because it is 1 1, and rank T is equal to the dimension of range should be equal to the W, and dimension of T, rank of T is equal to dimension of W, and this is same as dimension of V by the hypothesis. Now we will prove that T is non-singular. That is obvious thing. T is 1 1 non-singularity gives the kernel contains only 0 element. So from this you can get nullity T equal to 0 implies the dimension of null space of T equal to 0. Consequently, null space of T is equal to singleton set 0. That is contains only 0 vector. That implies T is non-singular. Okay. Conversely, if you have 1 implies 2. So this implies 1. This is nothing but 1 implies 2. Now we assume 2. T is non-singular. We have when you assume 2, that is T is non-singular, implies nullity T is equal to 0. Consequently, the rank nullity theorem shows that is rank T plus nullity T is equal to dimension of V, that is equal to dimension of W. That implies the rank T in this case, when T is non-singular, we can say that this nullity T is equal to 0. Then you can get rank T is equal to dimension V. But range of T is always a subspace of W, and the dimensions of the range and dimension of W are same. That implies range of T is same as W. This was T is onto. So T is onto. From this you can get T is non-singular, that is T is 1 1. So T is not 1 1 and T is onto implies T is invertible. So this proves 2 implies 1. That is 2 implies 1. Then we have 1 if and only if 2. Okay. Now we can prove this 1 is if and only if 3, and 2 is also if and only if 3. So that is we'll prove that by assuming 1 we can get 3 as well. What is 1? 1 is T is 1 1, and T is invertible. In fact, T is invertible. That implies T is 1 1 and onto. Consequently, T is onto. In particular, T is onto. So this proves 3. This is 1 implies 3. Now we will prove 3 implies 1. In 3 we assume that T is onto. That implies rank T is equal to dimension of W. It is given that this is same as dimension of V. Then rank nullity theorem implies that rank T plus nullity T equal to dimension of V implies It is given that rank T is same as dimension of V. You can get nullity T is equal to 0. Consequently, T is 1 1. Then T is onto and T is 1 1. That implies T is invertible. Okay, so we have proved that one if and only if 2 and one if and if 3, then we can say that these three conditions are equivalent conditions. Along with the previous three equivalent statements, you can incorporate two more equivalent statements for the same three conditions. That is, you can consider fourth and fifth statement to the previous with the hypothesis of the previous theorem. These two conditions are also equivalent to the proved three equivalent statements. So that means once you got this by the assumption that dimension of V is equal to dimension of W, then we have proved that there are three conditions. That is, one is T is invertible, and the second condition is T is non-singular. Then third condition is T is onto. So these are the three equivalent conditions we have proved just now, and we will prove that this 1, 2, 3 is also equivalent to this 4 and 5. So we will prove that this by assuming what is the implication of these statements. To prove 4, we have to start with the basis of V, and we'll prove that the images of that basis is also a basis. Okay, in this case, in the hypothesis of this. So we'll prove this 4. We start 4. Let alpha 1 etc. Alpha n is a basis for V. Then consider, then this is always what is the definition of basis? Basis means it spans V and these vectors are linearly independent. This is the definition of basis. And now we consider T alpha 1 plus etc. T alpha. Consider the vectors T alpha 1, T alpha 2 etc. T alpha n, T alpha 1, T alpha 2 etc. T alpha n. Then you can say that we will prove that this is the basis for W. To prove this, we assume 1. Okay, in 1 we have proved that. In one we have assumed that T is invertible, then T is 1, 1 and 1, 2. So if you assume 1, so we can prove this 1 implies 4, because if we assume 1 T is invertible, then T is 1, 1 and 1, 2. Since T is 1, 1, then T is non-singular. Then we have in the previous theorem we showed that is characterization of the singular non-singular transformations. Every non-singular transformation carries linearly independent set to linearly independent. Okay, so once you assume T is invertible, then T is 1, 1. Consequently, T is non-singular. Then T carries this linearly independent set to this linearly independent set. Then we can say that this is linearly independent. That is because every non-singular, this is the characterization of non-singularity, non-singular transformations. Non-singular linear transformation carries every linear independent set to linearly independent set. This is the theorem, linearly independent set. Okay, then we can say that this is linearly independent. And we have assumed that dimension of V and dimension of W are same, say n, then these n vectors is the basis for V, and this is a linearly independent subset of W whose dimension is also n. Okay, by assumption dimension of W is also n, so this linearly independent set spans W. On the other way, you can think of this an arbitrary vector alpha belongs to W. Then you can easily write this alpha as or we assume some beta belongs to W. Then you can easily hit alpha belongs to V such that T alpha equal to beta, because our assumption is T is on invertible, hence T is onto. Then any beta can be written as T alpha, for some T alpha, then this beta can be written as T alpha, and T of this alpha is an element of V, hence alpha is a linear combination of basis vectors, say x1 alpha 1 plus etc xn alpha n. So that is x1 T alpha 1 plus etc xn T alpha n. This shows that any vector beta belongs to W can be written as a linear combination of these vectors. So this form a basis. Okay, though any basis alpha 1 alpha 2 alpha n, there is a basis T alpha 1 T alpha 2 etc T alpha n. Okay, this is what this implies 1. This is nothing but 1 implies 4. Okay, then 4 implies 1 is also true. When we will prove that 4 implies 1. In 4 we have assumed there is a basis alpha 1 alpha 2 alpha n, not there is a basis. If there is a basis alpha 1 alpha 2 alpha n, then we can get T alpha 1 T alpha 2 etc T alpha n is a basis for W. Now to prove 4 implies 1, we need to prove that this T is onto and T is 1 1. To prove 4 implies 1, we start a basis of V. This is a basis of V. We start with the basis, and if we start a basis, you can get this T alpha 1 etc T alpha n is a basis for W. This is the assumption in 4. Then for any basis, if you start with any basis of V, you can get this condition. So we need to prove that T is invertible. Then T is how you prove T is invertible? T is invertible means we need to prove that T is 1 1 or T is onto. One of them is proved. Then T of alpha, we can easily prove that T of alpha equal to 0 implies T of some x1 alpha 1 plus etc xn alpha n equal to 0, because this alpha 1 alpha 2 alpha n has a basis. Then this implies C x1 T alpha 1 plus etc xn T alpha n equal to 0 implies each xi is equal to 0, xi equal to 0 for all I, because T alpha 1 T alpha 2 T alpha n is a basis for W. Then this is linearly independent, then each coefficient is 0. Then whenever T alpha equal to 0, we can get each coefficient equal to 0. Then this here this alpha is nothing but this one, this expression. So alpha is equal to x1 alpha 1 plus etc xn alpha n equal to 0 times alpha 1 plus etc 0 times alpha n, that is equal to 0. So this shows that whenever T alpha equal to 0, you can get this alpha itself 0, that is T is non-singular, hence T is 1 1. Since T is 1 1, we have already proved that whenever T is 1 1, then T is invertible using 2 implies 1. We have already proved that in the previous session. So we can say that this 4 also implies 1. Now we will prove 1 if and only if 5. In 5, we need to establish the existence of a basis alpha 1 alpha 2 alpha n with this condition. Alpha 1 alpha 2 alpha n is a basis, then T alpha 1 T alpha 2 T alpha n is a basis. So that is very trivial. If you assume 1, you can easily you can choose any arbitrary basis for V. We are given that V is finite dimensional, therefore there exists a basis alpha 1 etc alpha n is a basis, is any basis, any is a basis. Take any arbitrary basis of V, then you can get this T. We will prove that this T alpha and T alpha etc T alpha n is also a basis using 4. So using 4, you can say that T alpha 1 etc T alpha n is a basis for W. Okay, this is trivial because we already proved in the condition 4 that this whenever this alpha 1 alpha 2 alpha n is a basis, then this is also a basis. In 5, we needed to establish the existence of a basis, but we know that for every finite vector space there is a basis. Okay, so choose that basis, then you can get this result. Okay, so 1 implies 5. Now we assume 5. Suppose there exists a basis using the same argument. If you assume this basis, then you can get alpha 1 etc alpha n is a basis, and T alpha 1 etc. T alpha n, this is T alpha n. T alpha n is a basis for W and this is basis for V. Using the same argument you can prove that T alpha equal to 0 implies alpha equal to 0, that implies T is 1 1, hence T is non-singular, then T is invertible. So this is trivial. This is using 2 implies 1. So we can say that these 5 conditions are equivalent conditions. You can use any one of them to prove T is invertible in the case when dimension of V is same as dimension of W.